Good afternoon and welcome to this talk today, which will be delivered by Francesca Pianosi. I am Claire Etot from the Faculty's Industrial Liaison Office. If you have any questions for our speaker today, there will be a Q&A at the end of the presentation, so please submit any questions you have in the Q&A tab at the bottom of your Zoom screen. I will now hand you over to Francesca, who will talk about better handling of uncertainty in mathematical models, applications in the water and reinsurance sector. Thank you.
Thank you and good afternoon. So I'm a lecturer in water and environmental engineering at the University of Bristol. My area of research is mathematical modeling applied to environmental management problems, particularly in the water sector. And over the last few years, one area of research I've been very active in is the problem of how to handle uncertainty in mathematical models. So in this talk, I will give a brief overview of the background, the problems, where this is coming from, and the applications in industry that we developed so far. So mathematical models are increasingly used to inform decision-making in a variety of fields. For example, in aerospace or mechanical engineering, models are used to assist the design of complex structures or systems. Essentially, they serve as a virtual lab where different configurations of the system components are tested against different conditions, which is obviously much faster and cheaper than developing physical models, physical prototypes. Another example, maybe closer to my field, is mathematical modeling for flood predictions. So models are used to look at the likelihood of flooding in different places depending on climate characteristics, and then depending on the local characteristics of the terrain or the urban features. And these models can be used by urban planners, or, for example, they are used in the insurance sector to evaluate the risk and the exposure of potential clients. Another example, perhaps more in the news lately, mathematical modeling of epidemics, how that can be used to look at how a disease has spread across the population and to evaluate the effectiveness of different strategies to control an epidemic. So these are just 3 examples from very different fields. What is it that all these models have in common? I'm using a quite famous quote by the statistician George Box, who famously said that what models have in common is that they are all wrong. But hopefully some of them are useful, or at least can become useful if used in an appropriate way. So this is somehow part of the effort that we are doing with our research to make models more useful. But why are models so wrong? I'd say there are 2 main reasons. The first reason is that the data that we use to build and test mathematical models have errors and gaps, and particularly in the environmental field, this is a huge problem because we can't run experiments in controlled conditions as perhaps would be possible in other areas. In our areas, we just have to go out there and collect data, and this happens in a very noisy and messy environment. So one example that is very relevant, for example, for flood predictions. One variable we need in flood models is the stream flow, the amount of the volume of water flowing in rivers. And we usually do not measure continuously stream flow. So what we do is we measure the water level, and then we can map the water level into a value of volume by using some rule. And this rule is based on observations that were taken at some point by someone who physically went on a day and collected different measurements of level and flow velocity. And then from these measurements, we extrapolate a general rule to map level into flow. You can imagine how much uncertainty there is in this whole process because these measurements are very few or collected on one particular day. Maybe the cross-section changes over time, the vegetation grow or recede. So obviously, there are a long chain of imprecisions and inaccuracies. And so, for example, colleagues here in Bristol recently ran a study to look at what is the amount of error in flow, river flow data in England and Wales, and they come up with the numbers that range, depending on the place, between 20 up to even 40, 50% of error. And so when we use this data and feed them into our flood inundation models, essentially we really don't know how far off from reality we might be. These are problems we have in situations where we have monitoring stations. Then another huge problem is that actually there are so many places where we don't even take some measurements. So this is an example, a map from a colleague of the University of Kinshasa. This is the places where they measure continuously, currently at least, the water level in the river basin, and it's about 20 stations. And to give you an idea, this is 20 stations that are meant to cover a river basin that extend for almost 4 million squared kilometers. So huge gaps. We might ask ourselves whether maybe going ahead, these problems will be overcome, given that we now have this new amazing monitoring techniques. For example, a huge expansion relevant for the environmental field is that of satellite and remote sensing from satellite. For example, this is a picture that shows an elaboration of satellite image that tells us the soil moisture, so the amount of water in the soil during the 2013 drought across essentially the whole Europe. And this is amazing, of course, but is it enough? The answer is actually no, because, for example, this variable that we are inferring from satellite data here actually is the amount of water content that we have in the very top layer of soils. And now for practical applications, what we actually would need to know is the amount of water that is available throughout all the soil column, at least in the root zone, because this is what is relevant then for application for drought predictions, support of irrigated agriculture, and so forth. And this information we currently can only measure with in situ sensors that tell us about the water content at different depth, but in one specific place. So we have this trade-off where either we go for breadth and some depth, or we go for depth and then we only have very localized measurements. And this is just an example, but these kind of problems are extremely common in all environmental applications. The other problem is the other reasons why models are are so wrong is that unavoidably we have to make a number of simplifying assumptions. And this is the nature of the business. There is nothing we can do about it. Obviously, a model cannot be and should not be a one-to-one representation of the real system. But then the question is, how do we evaluate what is the right level, the appropriate level of simplification? And because of these problems I was talking about with the data that we use to then assess this adequacy, the question becomes tricky. And so, what are the consequences of all these uncertainties? I like to usually split this into two perspectives. So there is the perspective of model developers, could be researchers, or could be people working in consultancy that develop models for to sell to clients. The key problem probably is the difficulty of evaluating when and where a certain level of simplification is appropriate and where is not. So evaluate the modeling choices. For model users, so people who use model predictions to inform their decision making, maybe not necessarily knowing too much about what's going on in the model, they just use the output of the model. The problem of uncertainty is that not knowing how much uncertainty is there can easily lead them into either trusting model predictions excessively, more than they should, or in the lack of an information of how much uncertainty is there, just reject them completely and not use them. And obviously, either way, this is undermining the value of models and for their purpose. So my work and the work of a few other colleagues in our department here in civil engineering is to develop methods and implement them into practical tools to quantify and attribute the uncertainty of outputs of mathematical models. And I like to make this distinction between quantification, which is looking at the question of how much uncertainty is there in my model output. And this is an example for a model used in insurance. The model is used to predict what could be the expected loss from the portfolio of perils that the company insure with the different return periods. And what we do is with our methods is move from 1 point value prediction of this variable to a distribution, so that the user knows what's the range of uncertainty around that model estimate. And as you can see here, probably quite intuitively, the longer ahead we look into the future, so the longer the return period we use, the wider the uncertainty. The second question that we aim to address with our methodologies is the attribution question. So given that uncertainty in the output, can we map back and see which of the many uncertain input data and assumption is mostly contributing to the uncertainty in the output? So for example, a typical product of this kind of analysis might be a pie chart where we say, okay, looking at the annual average loss predicted by our model, half of this of the uncertainty in this variable comes from assumptions made about the vulnerability of the assets insured. And then the second contributor is instead around the assumptions made in modeling the hazard. And whereas perhaps the exposure data in this example are actually not too much important, and the same for a different variable. Why is this important? It's important, this piece of information, for at least two reasons. Number one, the quantification of uncertainty allows to make more robust decisions and avoid spurious precision, so trust in the model more than it should or less than it should, the model as is now. The other reason why it's useful is because it helps us prioritize the efforts if we want to improve the model by telling us what is, which inputs are mostly controlling the uncertainty in the output. It tells us where we should invest first into getting better quality data or testing more certain modeling assumptions, because that would lead to the highest reduction in output uncertainty. So, as I was saying before, we develop new methods, but we also develop tools, meaning software. So, in particular, we have developed a toolbox called SAFE, stands for sensitivity analysis for everybody, which is available in 3 different versions in MATLAB, R, and Python. So 3 very commonly used computing environment, and we published this software about 6 years ago, and we now have more than 2,500 users across different fields of engineering and earth sciences, and occasionally also some economics or social sciences for teaching and research purposes. And we also have a number of collaborations ongoing with industry. One is the one from which I took the example of the previous slide, working on transferring these methods to the reinsurance sector, where they can be used to analyze the uncertainty in these catastrophe models that are used to make a financial decision. The other one instead is an ongoing project with the water industry, where we use these models to look at the propagation of uncertainty through water resources models that are used for daily operations and for long-term planning of water systems. With this, I think I have concluded my talk, and I'm happy to answer any question. Thank you.
Thank you, Francesca. I just wondered if you'd be able to talk a little bit more about other areas of application for this.
Yeah, thank you. So, yeah, perhaps one thing that is worth mentioning, I work mainly in the water field and then insurance through floods, but the toolbox is and the methodology that are implemented is completely generic, so they can be applied to essentially any model. In fact, I have now also a little bit of collaboration within Bristol with aerospace and engineering researchers on using this kind of methodologies for supporting design of aircraft. And instead about the project in the water supply area, what we are looking at is now in particular how to use this kind of tools for what is now called risk-based planning. So water companies in the UK are now required to take into account explicitly of the uncertainty in predictions of water demand and water supply that they use to inform their planning. So we are looking at how this kind of methodology can help to do this in a consistent, structured way.
And I just wonder if, because obviously you said about sort of broadening out with different industry, how would you like to work with other industry in the future, sort of beyond this?
So at the moment, our model is we share the software. The software is open source, and we share it with a free license. What I made a discrimination between the academic users and others, because the difference there is that with the non-academic users, what we ask is for them to essentially sign a license that enables us essentially just to keep in touch in order for us possibly to get back to them and ask a few questions about, get some feedback about the use they are making of the software, and perhaps establish a bit more close collaboration. So if anyone is interested in going to this website, you will have access to a download form that is for researchers and students. But otherwise, if you just get in touch with me, and I'm assuming that my contact details will be shared, then you can request a copy under this license, but still with the free access to the code. And then usually we usually start from the tool to then explore together how this could be useful, and perhaps develop collaborations more widely.
That's great. Well, thank you, Francesca. I think this brings our session to a close. Thank you so much for speaking today, and thank you to everyone for attending as well. As Francesca said, if anything that's been spoken about today has captured your interest, please do get in touch. We will actually be contacting everyone after this week, and that will have our contact details. So then please do get in touch with us if there's any further information you would like, or any further conversations. But once again, thank you to everybody, and have a lovely afternoon. Thank you.
Thank you. Bye.